Good morning, everyone. Welcome to this lecture on semiconductor devices and VLSI technology. Let's do a brief recap of what we have done so far. Okay, so we studied about we looked about the crystal structure. Okay, we saw that the majority of our semiconductor devices are solid state devices, and in order to understand the properties of solids, right, whether it's a semiconductor device or a solid state device, you should know something about the solid state. Okay, how the solid state, the properties of the materials. We saw that all the material properties, essentially it finally boils down to how the atoms are arranged in the solid. We later saw there are different types of crystalline solids, and in silicon and some of the elemental semiconductors, silicon, germanium, okay, they comes to the family of something known as a diamond lattice. Okay, it belongs to the FCC lattice. It's a face-centered cubic lattice. Then we saw how the atoms are arranged in the silicon lattice. Then we discussed about the how to name the crystal planes and the crystal direction, because the properties, right, whether the electronic properties, whether it's a mechanical properties, whether chemical properties, it depends upon the crystal planes and the crystal direction. Then we saw about, okay, in order to, because in the solids the atoms are arranged very very closely, and there are interatomic interactions. For example, okay, you cannot decouple the electron in one atom to the electron in another atom. Okay, so that is, it's very different from a gas or something. Okay, so that is why in order to have a proper theory of solids order, one needs to wait till the early 20th century. Okay, that is when we had the quantum mechanics and quantum statistical mechanics. We went through the different postulates of the quantum mechanics, and then we solved the Schrodinger equation in some simple cases, like the infinite potential well, the finite potential well, so the tunneling barrier. Then we saw, okay, what happened. Then having understood all those things, okay, we come to solids, okay, where electrons are arranged, or the crystalline solids where the electrons are arranged in a periodic fashion. So we saw that, okay, when we try to solve the Schrodinger equation on a periodic potential well, we will see something known as the energy bands. So in the infinite potential well and the finite potential well, the energy levels are all discrete. But once it comes to a periodic potential well, there are bands of energies, and then there are gaps in energies. Then we saw that in a solid, okay, there are at 0 Kelvin there are many bands. Then the topmost completely filled band we call as a valence band. The one band which is above the valence band, which call as a conduction band. So depending upon the band gap of the material, the electrons may go from the valence band to the conduction band at room temperature, and then they leave the vacant states behind. We saw that the vacant states, again, rather than take into account of all the electrons in the valence band, okay, we could get the same result if we focus on the vacant states, but if we assign it a positive charge. Okay, we call those quasi particles as holes. So okay, so now let us come to, okay, so let's try to calculate, okay, how many electrons and holes are there at equilibrium in a piece of semiconductor. So we saw that, okay, the atomic density of silicon is, okay, 5 into 10 to the power of 22 per centimeter cube. Okay, if we try to, okay, if you say that, okay, there are 4 valence electrons, okay, 4 valence electrons in silicon, okay, it's not like, okay, so this is wrong. Okay, so if you try to multiply 4 into 5 into 10 to the power of 22, okay, that will give you a wrong result. In fact, the number of electrons, free electrons in a silicon crystal is actually far lower compared to this number. Okay, in order to compute that number, okay, what we are going to do here, we are going to take a homogeneous material. Okay, homogeneous material is that, okay, the atomic composition is spatially constant. Okay, all right. So it's a pure pristine silicon crystal. Let's assume there are no defects. Okay, there are no defects at all. Okay, in reality we will see defects. Okay, sometimes we even introduce defects. Okay, we will see that in the next lecture. So let's assume the atomic composition is spatially constant, right? So that means, okay, there is no internal electric field, nothing is there. Okay, so spatially it is constant. And also we consider the system under equilibrium. Okay, so this is an important concept, equilibrium. So what does equilibrium means is that the macroscopic properties, okay, the macroscopic properties, if you try to measure a current or voltage or something, okay, so they don't change. Okay, in fact, if you take a semiconductor bar, okay, and you connect something like an ammeter here, okay, and you measure this one at equilibrium, okay, when the system is under thermodynamic equilibrium, okay, the current is 0, okay, so this will give you 0 reading, all right. So that means, okay, there is no energy transfer, there is no particle transfer to the outside, okay. So there could be, okay, so internally at a higher temperature, okay, there could be atoms moving inside the solid. But we saw that, okay, we saw that from the EK diagram, okay, for every, this is symmetric, okay, for every electron here, there is another electron here, which has a negative opposite velocity, so they cancel, okay, that is why the net current equal to 0, right. So later we will see some other concept also, okay, we will see, okay, what is known as a steady state, okay. So, okay, let us start with only equilibrium because that is the simplest of all cases, right. We will see what is the difference between steady state and equilibrium later. Now, our goal is to calculate the carrier concentrations under equilibrium, right. Our goal, okay, whether it's electron concentration or hole concentration, this is what we are trying to do, okay. So, but in order to find the carrier concentration, we need to know two things. One, we already know that, okay, there are bands like a conduction band, there are bands like valence band, okay. So we know that there is a conduction band, valence band. We don't need to worry about the bands below the valence band because they are all full. So essentially we need to concentrate on the conduction band and the valence band. So this is against energy. So in order to calculate the number of electrons in conduction band or the holes in the valence band, first what we need to know is that the distribution of energy states within the band. So for example, okay, if you go higher in energies, okay, we don't know, okay, suppose we want to place an electron, okay, how many positions are there, right? And the second thing is that, okay, so what is the probability of an electron to occupy that state? So we need two things, okay. One, we need the information about the energy states, available energy states, okay. This has a technical term, it is known as density of states, okay. So density is the density of available states. The other thing is that what's the probability of each of these states being occupied by an electron or a hole. So we need these two, essentially we need these two quantities. This is, okay, if you examine this one, okay, this is very similar to counting the number of people in a stadium or something. For example, this is a Wimbledon center court. So here you can see all right. So you can maybe we may assume that this is like the band gap. Okay, nobody sits inside the court, right? Except for the players and the people who are assisting the players. So all the audience, okay, all the people who are the spectators, okay, they don't see, none of them sits inside the court. So they all starts from here. Okay, so you can assume, okay, let's assume this is the conduction band, right? So the first seat starts from here, right? Then people start sitting along the seats, right, like this one. So you can see here, okay, closer to the center court, okay, so you can see that the number of seats are very small, okay, very small, smaller, and they are more maybe expensive seats, right? As you go higher, you can see the number of seats goes up. Okay, the number of available seats goes up, and there are more people sitting away from the center court, right? So it is very similar to what is there in conduction band. Okay, so the closer to the band, okay, so there are some seats. Then away from the bottom of the conduction band, there are other seats. Then the question is, okay, okay, so what is the density of seats? How many seats are there? For example, how many seats are closer to the court? How many seats are away from the court? Okay, once you know those numbers, okay, then we can multiply by how many seats are there. Then you can find if all the seats are occupied. Then the question is whether all the seats are taken or not. That's how you can see. That's you can calculate the number of spectators at any time inside the stadium, right? So inside the silicon, okay, if you look at this one, okay, so the density of states, okay, so people can calculate, okay, they can calculate. It has a peculiar shape like this one. So that this is the bottom of the conduction band. Okay, this line is the bottom of the conduction band, and similarly this line is the bottom of the valence band, and this is the energy gap. Okay, this is the energy gap. As you go higher, okay, so this has a shape, the green line. Okay, it follows the green line. that's a shape, that's the available number of the states. For example, the number of available states increases, then it decreases, then again it increases, and it decreases finally, right? Okay, so this is then, so this is the, okay, so this is similarly valence band also, okay, it increases, it decreases, then again it increases, like this one. Okay, this is the width of the valence band, right? But what we are going to do is that, okay, we are going to do something known as a parabolic approximation. The parabolic approximation is that, okay, because this is if you take this exact shape of the density of states, it's very difficult to compute that. So what we do is that, okay, we approximate this by a parabola. Okay, this is a parabola like this one, this red line like this one. Yeah, so we assume, okay, that is because, okay, so this assumption, we will see why this assumption is taken, okay, because most of the electrons will be at the, for example, electrons will be at the bottom of the conduction band. Similarly, most of the holes will be at the top of the valence band. Then we are taking this approximation, this is known as a parabolic approximation, right. So the reason for this parabolic approximation is this one, okay, you can calculate, okay, this also comes from the solid state physics. I am not going to derive this one, okay. So for a free particle, right, you can derive the density of states expression, right. You can look at the textbook, the Donald Neumann, you can see that I am only giving the result here. So depending upon there is something known as the dimensionality of the system. For example, it's a three-dimensional system. Okay, three-dimensional system, the particle will, okay, so this particle is able to move any of these direction. For example, x, y, and z direction. Then there are some other systems where the particle is free to move only in two directions. For example, this particle is able to move only in this direction or this direction. Okay, so this is actually known as a two-dimensional quantum well, right. So in the two-dimensional quantum well, okay, the particles are confined. Okay, for example, if this is the z direction, okay, the z direction, the particle is not able to move, that is known as confined. Okay, it is able to move in x and y direction, right. So those are two-dimensional quantum well, and there are other, the other one-dimensional system is a quantum wire. Okay, in this quantum wire, the particle is able to move only along the length of the wire, it's not able to move along the other direction. And then the last, okay, it's a zero-dimensional system. It's actually a quantum dot. Okay, it's a dot. The particle is confined in all direction. So you can derive the density of states expression assuming the particles are free particles. Okay, there is an analytical expression. For example, in the three-dimensional system, okay, it has the shape of a parabola like this one. In the two-dimensional system, it's a step kind of a distribution. So in this case, it is like a 1 over root expression, and these are all finite levels. Okay, so these are like the finite energy level. So what we are going to do is that, okay, we will take this expression. Okay, that is why it's called parabolic approximation. We take this result. Okay, we take this result and use it in the context of silicon, right. So even though it is not exact, but at the bottom of the conduction band and the top of the valence band, this is a good approximation. So the expression for the density of states as a function of energy, it looks like something like this one. So it is, okay, this is Mn star, there is an Mn star. Okay, so this is actually the density of states effective mass. Okay, we saw the effective mass in the previous case. Okay, effective mass is a kind of an approximation, and we saw that there are different types of effective mass: conductivity effective mass, density of states effective mass, band structure effective mass. The band structure effective mass is nothing but the curvature. Okay, it is related to the curvature of the EK diagram. So this is known as the density of states effective mass, and so density, so then it is proportional to under root E by EC. Okay, so this is the term. Okay, this is E. So as E increases, okay, this is EC. Okay, this is E minus EC. Okay, that is this delta. Similarly, density of effective mass in the valence band also we can do something like this one. This is a density of states effective mass for the holes, and this is H cut is equal to H over 2 pi. And okay, this is EV minus E. Okay, so EV minus E, that is because, okay, this is the energy axis. Okay, so this is EV minus E. That is the bottom. This is EV here, and this is E here. Okay, like this one. And in this case, okay, it is E here, EC here, and this is so EC is the bottom of the conduction band, EV is the top of the valence band, and E goes in this direction. So this is a EK diagram. Okay, this is EK diagram. So once we have these two things, okay, so we know how are the seats. Okay, so essentially the density of states, as I mentioned, okay, this is the distribution of the seats. Okay, this is the distribution of the seats for electrons and holes. The second thing what we want is a probability, how these seats are filled. Okay, by what rule are these seats filled? So for that, okay, we need to examine, okay, what are electrons. Okay, so electrons are not similar to gas molecules. Okay, they are different. Okay, they are quantum mechanical particles. They belong to a category which are known as fermions, right? So the fermions, so they are spin half particles. Okay, so for example, okay, they are very different from photons and phonons. Okay, we will see phonons later. They are the quanta of the lattice vibration. The photons, okay, the photons and phonons, they come under the category bosons, right? So the electrons, the main difference between electrons and bosons is that, okay, they follow something. Okay, you might have studied in your chemistry, +1 or +2 chemistry, Pauli's exclusion principle. Okay, so that is, if you have a quantum mechanical state, okay, if you take into account of the spin also, each allowed state, okay, can accommodate only one electron, right? So that's a rule for electrons. Okay, so if there is a state, okay, where you are tracking the spin also, only one electron can sit in that state, right? For the next electron, okay, it should go to the next state. So it is very different from the center code. Okay, for example, at any horizontal level, there are many people can sit. Okay, so that is very different. Okay, in the case of electrons, okay, if you define that as a quantum mechanical state, okay, at one position only one electron can sit. Then okay, if you look at the, okay, so this is how, okay, so this is so the electrons follow something known as a Fermi-Dirac statistics. Okay, so that's a rule you need to follow. Okay, these electrons need to follow for at any energy level. For example, the probability of finding an electron is something like this one. This is a probability f of E, right? It's 1 by 1 plus exponential E minus EF by KT. Alright, so okay, so this EF, okay, it has got a term. Okay, it is okay, in some it's known as a chemical potential or the Fermi level. So now let us look at, okay, what is the definition of a Fermi level, okay, for a chemical potential. If you say that, so if you have a given system of electrons with a chemical potential mu, okay, I will come to what is chemical potential. The probability of a state with an energy E occupied is given by this one. Okay, it's similar to a previous expression where mu is equal to EF. Now let us see what is chemical potential. Okay, chemical potential is actually the change in Gibbs free energy. Okay, Gibbs free energy when a particle is added or removed to the system. Okay, so if you have a collection of system, and if you track the Gibbs free energy, okay, Gibbs free energy is actually, it means the available, okay, that is the amount of energy which is available to convert into work, right? So if you have some system, some thermodynamic system, and some energy is there, you cannot convert that entire energy into work. Only some portion of that energy can be converted into work. That energy is actually known as the Gibbs free energy. So when you add a particle or remove a particle to a system, the Gibbs free energy changes. Okay, so then what is the change in the Gibbs free energy with the number? Okay, so this is actually the mu or Fermi level, what we call. Actually, it's a chemical potential. So the Fermi level, okay, the Fermi level or the Fermi energy is actually the chemical potential at a temperature T is equal to 0 Kelvin. T is equal to 0 Kelvin. You might have also studied the Fermi level. For example, if there are metal, if you take a metal, okay, so you at 0 Kelvin, there are all these energy levels are fixed. Okay, so what is the topmost occupied energy state for metals? That is also called the Fermi level. But this definition, okay, this definition is not true for semiconductors or quantum wells. Okay, for example, we will see later. Okay, so suppose there is a quantum well like this one. Okay, these are different energy states, and this state is fixed, this state is not fixed at 0 Kelvin. Okay, then the Fermi level, okay, so this is very different from metal. Okay, the Fermi level lies exactly at the middle of the topmost filled state and the bottommost unoccupied state. Okay, so this is where the Fermi level is. Okay, so in the case of structures with the bands like this one, okay, bands like this one, So, the Fermi level lies between the topmost filled band and the bottommost unoccupied band, okay, somewhere between. Okay, so this is the difference between metals and semiconductors, or metals and quantum wells or quantum dots. So, in the semiconductor textbook, okay, we rarely see this term chemical potential. Okay, we normally use the word the nomenclatures the Fermi level. So, the Fermi level, the semiconductor textbook, we typically use the EF instead of the mu. Okay, although strictly they are true only at 0 Kelvin. Okay, we assume they are both are identical for all temperatures. Okay, so this is something if you look at any chemical engineering textbook versus a solid state or semiconductor textbooks, okay, this is we normally use Fermi level. Okay, they use chemical potential. Okay, so what is the in the case? Okay, so you may wonder, okay, what is so important about chemical potential in the for electrical engineers? Okay, suppose for any device, okay, if you have a device with many terminals, okay, and if you apply voltage here, so what that voltage does is that, okay, it can raise the chemical potential up or down, whether it's a positive polarity or negative polarity. Okay, this is very important. Okay, this is very so that is what the bias, the voltage source does is, okay, it raises the chemical potential at that point. And other thing is a very important thing is this one. Okay, for example, if you connect a voltmeter, okay, if you connect a voltmeter between two terminals of a device, okay, for example, you take any device and you measure this potential using a voltmeter. What the voltmeter really measures is actually the difference between the levels of chemical potentials or the Fermi levels. That is what it does. It's very, very important for this one. So, that is very important. Okay, so whenever we try to connect a voltmeter to a device, it measures the difference in the chemical potential. For example, this terminal A, this is B, the VAB is actually is nothing but the difference between, okay, it is proportional to the difference between the chemical potential A minus chemical potential B. That is very important. Okay, we will see, we will use this concept later, right? All right, so that is about the chemical potential or the Fermi level. Now, we have both the terms. Okay, we know the density of states and we know the Fermi level, right? Now, we are able to calculate the equilibrium, the carrier concentration under equilibrium. So, now let us see how does this plot looks like. Okay, so that is also very important. Okay, so this is something we have seen in students. Okay, okay, they are able to write the mathematical expression, derive mathematical expression, but it's also very important to know how the plot looks like. All right, so for example, the Fermi Dirac function. Okay, the Fermi Dirac function. Okay, if you try to plot against E minus EF by KT, it will look like something like this one, right? So it's a probability. Okay, so that means, okay, if you so it should be between 0 and 1, the probability, and this I am varying the energy. Okay, energy E minus EF by KT, right? So you are changing by the amount of KT. Okay, for example, this is 1 KT, 2 KT, 3 KT, like this one. Similarly, this is minus 1 KT, minus 2 KT. Okay, so here energy is going below the Fermi level. So you can see this is actually a symmetric function at 0 Kelvin. Okay, so this is a symmetric function, right? And you might have studied about in the case of gases. Okay, you might see the Maxwell-Boltzmann distribution. So the Maxwell-Boltzmann distribution, for example, you can see that's also plotted here. So if the E minus EF of KT is actually around more than 3, okay, so in this range, okay, you can see that the Fermi Dirac distribution and the Maxwell-Boltzmann distribution, okay, merges each other. Okay, we will use this approximation later. But if the E minus EF is very small, right, essentially when your energy of an electron is closer to the Fermi level, you can see there is a discrepancy. Okay, you should not use this Boltzmann approximation. The Boltzmann approximation is nothing but this one. Okay, you approximate like this one. Okay, so we neglect the term 1. Okay, so MB approximation, okay, is essentially f of E is equal to 1 by, you neglect the 1 in the denominator. Okay, exponential E minus EF by KT, right? So this is a Maxwell-Boltzmann approximation. And if you vary the temperature, what happens is, if you look at the temperature, essentially the shape of this one is the same. But at E is equal to EF, okay, essentially the probability is half. Okay, so for an electron to occupy at E is equal to EF is half, but the only difference is that when you the shape is different at a different temperature. For example, is 1200 K, 900 K, 600 K, 300 K, like this one. So that's how the distribution changes. So now let us so we learned a lot of concepts. We learned a lot of basic concepts in solid state physics. Let us try to take a quick recap of all these concepts before going into calculating the electron concentration. First thing is that this I am repeating because this is very, very important. Alright, so because just normally we have seen that we start this course or we talk about all these things. So midway to this course, students may start wondering, where does this conduction band and valence band come, right? So now let us see, so the mechanical, electrical and chemical properties of solid depends upon atoms, how atoms are arranged in solids, and they also depend upon the crystal orientation and direction. That is very important. Alright, so that is why it is very important to know the crystal structure. All the properties of the mechanical, electrical and chemical properties, you can relate directly to the how the atoms are arranged. Then other important concept, we saw that the energy bands and gaps. This is not something which was there in your +1 or +2, where there you had only the shells, all the electrons, so the Bohr model and all those things, they were discrete energy levels. But what we have is here, suppose in the case of crystalline solids, when you solve Schrodinger equation in a periodic potential well. Why is there a periodic potential well? Because atoms are arranged in a regular solid, in a periodic fashion, because there is the atomic distance or the lattice constant is same, one atom to another atom. So that is why you have a periodic potential well. Then you see that you have discrete bands of energies and you have discrete gaps of energies. The other important concept is the concept of holes. That is, you get the same result. The dynamics of the whether you track the large number of valence band electrons with negative charge or small number of vacant states with positive charge, you always get the identical result. So then it is easier to track less number of particles, rather than large number of particles. So we call those particles as holes. So you have to always keep in mind that the holes are quasi particles, right? You cannot go and put a hole on a, suppose you have a very sophisticated weighing balance. It can measure the mass of an electron. It's not possible for you to put a hole on the balance and see what is the weight of the hole. That is because holes cannot be emitted to vacuum. That is very important. They can be only observed in the valence band of a solid. You can move the hole from the valence band of one solid to another solid. That is all possible. We will see later in devices. We typically move the hole from one valence band to the other valence band. That is all possible. The next important concept we saw was effective mass, right? The effective mass is that, so in a solid, the electrons move in a periodic potential well. So then what effective mass is approximation does is that you don't need to worry about the periodic potential well, you don't need to worry about the quantum mechanics and all those things. The provided what it does is that you can treat the electrons and holes semi-classically, provided you change the mass from its free space mass to the appropriate effective mass. This effective mass could be different from one material to another material. It could be different at higher energies. It could depend upon the direction in which the carrier is moving. But it will simplify your equations a lot, right? But keep in mind, this is an approximation, right? So this is a good approximation which we are taking in this engineering. So this approximation, so what it helps is that it helps the electrical engineers to perform device analysis with a minimal use of quantum mechanics. Right, so they don't need to worry about, they can totally forget about all the quantum mechanics, Schrodinger equation, periodic potential, provided they change the effective mass from the free space mass of electron to the appropriate effective mass of that material. The last concept which we saw was the Fermi level. The Fermi level is actually the energy of the topmost electron in metals. That is important. In the metals, it is a topmost occupied at 0 Kelvin. When the conduction band is partially filled, that happens in metal. But in the case of semiconductors and quantum wells, with the discrete energy states or discrete energy bands, the Fermi level at 0 Kelvin typically lies halfway between the highest occupied energy level and the lowest unoccupied energy level. This is very important concept. How the energy level at 0 Kelvin is very different from in the case of metals and semiconductors. Another important concept is for a device with many terminals, okay, the chemical potential, okay, chemical potential can be raised or lowered by the application of bias. This is very important, okay. So, this is essentially when we draw the energy band diagram of a semiconductor device and when we start applying the voltage, okay. So, you need to remember this concept, okay. So, that's how you, suppose you draw the energy band diagram at an equilibrium and you are asked to draw the energy band diagram under a bias, or for example current is flowing, okay. So, then this is a very important concept. And other thing is that, okay, in a semiconductor device or a solid state device, okay, when you connect a voltmeter and try to measure the potential between two leads, okay, what it truly measures is actually the difference between the levels of chemical potential, right. So, it is not always the electrostatic potential, we will see there is a difference, okay. So, there could be an electrostatic difference, potential difference between two ends, but the voltmeter may read 0, okay. So, we will see that example, okay. So, we will, then we will will try to bring in this concept again. All right. Now, having learned about all this concept, I think we are ready now to calculate the electron concentration in the conduction band, right. So, our goal is to calculate the number of electrons in the conduction band, right. So, for that we require two things, okay. One is actually the density of states, okay. One is actually the density of states, other is the probability from the Fermi Dirac statistics. So, if this is a conduction band if this conduction band is like this one, okay, and this is the bottom of the conduction band, this is somewhere is the top of the conduction band, okay, you see top. All we need to do is that, okay, it's a symbol, okay. So, we see that how many states are available at each energy level and what is the probability of an electron to occupy that energy level. Once you multiply that, then what we are doing is we are going to do an integration from the bottom of the conduction band to the top of the valence band. That's all. Now, let us put all those things, okay. The density of states effective mass is actually it is, okay, some k into root of E minus EC, okay, that is this term, right. And the Fermi Dirac probability is 1 over exponential this one, okay. So, this is integral, okay. So, all these terms, okay, it actually comes from this k term from the density of states, right. So, now our goal is to do this integral. Actually, it is this integral, okay, if we try to calculate exactly, it is very difficult to do, okay. So, what we are going to do is we are going to do some approximations, okay. First thing is that, okay, the width of the conduction band, okay, actually what we are going to do is that, okay, we are going to take the EC top, okay, we are going to take the EC top to infinity, alright. So, anyway, you won't find any electrons there, okay, at the EC top, okay. So, it does not matter if you go integrate all the way to infinity, right. Then what we can do is that, okay, we can take, okay, E minus EC as some kind of a variable, okay. So, we can take some variable as y or something, right. Then this integral, actually this integral goes from 0 to infinity. Then one more approximation what we are going to do is that, okay, this is known as a Maxwell-Boltzmann approximation, we saw it earlier. When the electron energy level and the Fermi level, okay, this one, all right. So, if this is large, okay, this is large, okay, you can neglect this one, all right. So, essentially we assume that from the Fermi level, okay, Fermi level to the bottom of the conduction band, it lies more than 3 kT, Then if you don't do this integral, okay, so what happens is that, okay, so it is very difficult, right. So, if you do this integral, okay, it's essentially this is the gamma function, okay, you can use this gamma function, then this integral you can get a closed form expression, right. So, I am only showing the result, okay, you can try to do this integral yourself, it is a simple integral, only thing is that, okay, you need to use this result, you need to use this result, okay, it comes from the gamma function. Then the number of electrons in the conduction band, okay, it will look like something like this one, okay. Some prefactor is there, NC, then exponential minus EC minus EF by KT, right. So, the EC minus EF is actually, okay, so this is EC, this is the bottom of the conduction band, and where is your Fermi level, okay. So, the Fermi level in this case, okay, it is assuming the Fermi level is below the EC, right. And also we did an approximation that the Fermi level is at least away by 3 kT for this case. Then you can get a closed form expression like this one, right. So, this NC is actually, it is actually known as the effective density of states in the conduction band. So what this expression does is that, okay, so there are a lot of states in the conduction band. What we are going to do, we are collapsing all the states and we are putting all the states somewhere close to the bottom of the conduction band. Okay, we are calling this as the effective density of states. It's as if all the electron, there are so many seating positions available which are close to the bottom of the conduction band. Okay, so that is why it's called the effective density of states in the conduction band. And all the electrons, okay, all the electrons are sitting very close to the bottom of the conduction band, right? So on the other hand, okay, if you are not doing this the Maxwell-Boltzmann approximation, right? So that is when the Fermi level is comes in close vicinity of EC. Okay, so for example, it is very close. Okay, so then you cannot take this approximation. Then you need to invoke something known as a Fermi integral. Okay, so this is actually, you need some kind of a tables to calculate this one. Okay, this is a Fermi integral. Okay, so these are, so then you can write the expression for electrons, something like this one. So for that, you need to always refer to the Fermi integral table, okay, in order to calculate this value. For example, E minus EC by KT is this one. Okay, in such a case, what is a Fermi integral? You consult the table and you need to, that's how you calculate this. So in some cases, okay, when the Fermi level is very close to the bottom of the conduction band, you may have to resort to Fermi integral. But you should know this one. But in real devices, sometimes, okay, the Fermi level may come very close to EC, and sometimes we will see later, okay, it may go inside the conduction band, right? So in such cases, okay, this is wrong. Okay, this expression is wrong. You need to use this expression. But in typically problems, whether it's a chapter back exercises or in quizzes, we won't give you problems where this Maxwell-Boltzmann approximation is not valid, right? That is because it is difficult to consult tables during the exam, right? But you should always know. Okay, so whatever, this is very important for any course, right? Suppose you have an expression or something like this one, under what region that expression is valid. Okay, where this is valid, what's the region of validity? If the region, if you are crossing that region of validity or that boundary, what is the correct expression to use? I hope that is clear. You can do a similar exercise for holes in the valence band, right? The holes in the valence band is also the similar. For example, all you need to do is that, okay, so you need to calculate, okay, what is the density of states at particular level. Then other important thing what we need to do is, okay, we need to find at that state, okay, whether what is the probability for its being vacant. That is very okay, so because we are trying to calculate counting the vacant states. Okay, so this is the main difference between the in the case of the probability in the conduction band, okay, and in the case of the probability in the valence band. In the valence band, we are looking for the vacant states. Okay, that is why we are calling 1 minus f of e. Okay, so 1 minus f of e is the probability of that state being vacant. Then, okay, it's the same thing. Okay, we start with the bottom of the valence band. Okay, so the valence band is like this one. Okay, this is energy gap. This is the conduction band. This is EV. So valence band is all the way here. Okay, so we need to do this integral from the bottom of the valence band to the top of the valence band. So just like in the case of in the previous steps, what we did, okay, so we tend this to infinity. That is the bottom of the valence band goes to infinity. This is EV here, right? Then if we do the same thing, same approximation, for example, the Maxwell-Boltzmann approximation, that is the Fermi level. Okay, so this is EV. Okay, this is EF. EF is at least 3 kT away from the top of the valence band. Then, okay, we get a similar expression. Exactly, the terms look identical. Okay, we can switch from the subscripts for electrons to holes, right? Again, this term, okay, this term is actually the NV is actually the density of states in the valence band. So similarly here, okay, so if this is a valence band here, okay, most of the holes are at a close proximity of the top of the valence band. Okay, so it's as if you take all the holes and it's as if you create large number of states at the top of the valence band, and all the holes are occupied there. And this is the density of states, effective mass of holes, like that. So these are some numbers. Okay, so these are not some numbers. There is still some debate about what are these exact numbers. Okay, so but I think let us see. That is why you may see some slight variation between these numbers between textbooks. But at least you should know the order of these numbers. That is very, very important. So you can see the silicon. This is essentially these are all at room temperature. In silicon, the effective density of states of at the conduction band is around 10 to the power of 19. Okay, the holes are also around 10 to the power of 19. Okay, that is why this is very important. Okay, so you can see, okay, the NC and NV, they are roughly around 10 to the power of 19 per centimeter cube, right? And these are some for some other materials, for example, like gallium arsenide, okay, so and germanium. Okay, so for silicon and germanium, they are roughly in the same number. Okay, gallium arsenide may be actually around one order lower. So you need to remember at least this expression. This expression is important. Okay, similarly, the electron, the whole electron and the hole concentration, the density of the carrier concentration, the electrons, this one. So these two things. Okay, so you may not need to know this expression, but at least you should know there is a temperature term inside this one. Okay, that is important when you vary the temperature, right? So that is okay. So others are all constants. Okay, so this expression, this formula, and this formula you should know. So we typically give you don't need to remember the number of the exact value of these numbers. Okay, because we typically give that for the quizzes and the exams. But you should remember that is one thing is that this order is also very important. The order you should know, because that is very important. In the first class I mentioned about the sense of numbers, right? Whenever you do a multiplication, when you do a calculation of something, you get some result. By looking at the answer, you should make whether my answer makes sense or wrong. All right. So now let us see. Okay. So having learned about how to calculate the electron and hole concentration, let us take the case of an intrinsic semiconductor. In the intrinsic semiconductor, that is it could be considered as the most purest form of material. Okay, it is okay. So you cannot take, okay, so this is something, okay, you do a lot of chemical processing and you create intrinsic semiconductor. Okay, intrinsic semiconductor, it consists of only, for example, silicon, it consists of only silicon atoms. Okay, let's assume there are no defects, or that number of defects are actually far lower than your detection limit. Okay, your detection capability. So in an intrinsic semiconductor, okay, what we have, okay, so you have, okay, so this is the conduction band, this is the valence band, right? So at any temperature, okay, we saw that at 0 Kelvin, okay, this is full, this is empty, right? At 300 Kelvin, what we saw, okay, so you have these electrons here, okay, it may go to here, okay, they may go here. Whenever an electron goes from valence band to conduction band, it leaves a hole behind. Okay, so you have an electron here, you have an electron here, you have an electron here, you have a hole here, hole here. So in an intrinsic semiconductor, all right, so whenever there is an electron created, there is a hole also created. So they always form in pairs. Okay. So the electron hole pair generation in an intrinsic semiconductor, that is due to thermal generation. That is because the electrons in the valence band, they can get some energy from thermal energy, and it can get excited and go into the conduction band. So they always form in pairs, the electron and holes. So that means the electron and hole concentration at any temperature should be the same, right? So we can equate the electron concentration expression we derived earlier, and this is the density of holes. You can equate these two things, right? So if you do this one, all right. So yeah, what you do, you rearrange these terms. Essentially, what you do is that, okay, you move the NC to the NV to the other side, then you take the log of that thing, then you can get. So if you do this one, you can derive the expression for the Fermi level, right? The Fermi level is nothing but EC plus EV by 2 plus KT by 2 ln of NV by NC. Okay, we saw that NV and NC are very close, okay. So if you look at this number, okay, they are around 2.863, they are very small. So this term is actually very close to 1. Okay, this is very close to 1, right? Very close to 1. So then the Fermi level, okay, Fermi level can be written like this, and EC plus EV, this is EC, this is EV. So EC plus EV by 2 is actually the middle of the band gap, So the Fermi, and this number is very close to 1. That means that for an intrinsic semiconductor, the Fermi level lies very close to the middle of the band gap. This is very important, right? So this, and if you put T is equal to 0, if you put T is equal to 0, okay, is essentially at the middle of the band gap. All right. So this is, so you can see this is in sync with the earlier Fermi level definition. We saw that, okay, in the case of systems with the discrete energy bands at 0 Kelvin, we saw that the Fermi level lies between the top of the occupied level and the bottom of the unoccupied level. This is exactly half. So this is what essentially we get. The Fermi level, okay, lies at the middle of the band gap. For any other temperature also, for any other temperature, if you increase the temperature of the intrinsic semiconductor, what happens? This number is very close to 1. Okay, this number is T is increasing, but this temperature is very small. So it will still lie very close to the middle of the band gap. Then what you can do is that, okay, once you know the Fermi level, okay, you can calculate what is the intrinsic carrier concentration. That is, because we saw that the electron and the hole concentration are the same in an intrinsic semiconductor. That is because they are generated in pairs. Then you can do this one. Okay, essentially, once you equate these two things, from here you can calculate what is the N and P concentration. N and P concentration is like this one, right? So root of NC/NV into exponential minus Eg by 2 kT, right? Once you know the NC and NV values and the Eg value of this one, okay, you can try to calculate the intrinsic carrier concentration at any temperature. So if I try to plot, okay, if you try to plot this function as a function of 1 over T, that is very important. Okay, that is because of this term. Okay, that is because of this term. Essentially, okay, so essentially this slope is roughly proportional to Eg by 2. Okay, it is close to Eg by 2. It's not exactly Eg by 2. So you can see this is 1 over T. 1 over T means, okay, this is something known as an Arrhenius plot. You might have seen in chemistry or something. Okay, so here I am varying the temperature. Okay, I am varying the temperature means at very high temperature, very high temperature. That means that is in this region. Okay, when T is large. Okay, when T is large, okay, as T increases, okay, this goes in this direction. As T decreases, okay, it goes in this direction. So when you increase the temperature, what happens? There are a lot of thermal generation. Okay, there are a lot of thermal generation. There are a lot of holes and electrons. You can see it comes to here. Okay, it increases. Okay, it increases exponentially. Okay, it increases exponentially, and the slope, okay, these are shown for different materials. You can see germanium at the top, silicon at the next, gallium arsenide. So at any temperature, for example, I take a line like this one. Okay, it cuts germanium first, then silicon, then gallium arsenide, then gallium. So the reason is that, okay, the band gap, okay, it comes from the band gap, right? So for example, the band gap of germanium is actually less than band gap of silicon, less than band gap of gallium arsenide, less than band gap of gallium phosphide. That is the reason. Okay, that is the reason the intrinsic carrier concentration, if you look at the previous term, it is proportional to minus exponential minus Eg. So if the band gap is large, Ni will be low. Okay, so that is the reason. And similarly, the slope, the rate at which also increases, also it depends upon the band gap. So you can see you may have different materials, okay, which have different electrical conductivity at a room temperature, but when you increase the temperature, okay, essentially what happens when you at a sufficiently large temperature, okay, so they may all have a similar conductivity or close to similar conductivity. And this is the reason. Okay, so this is the reason. Another thing is that as you increase the temperature, what happens is that number of carriers are increasing. Okay, so that means, okay, if you take a semiconductor bar, okay, pure intrinsic semiconductor bar, and if you do an Ohm's law measurement, that is, you are trying to measure the resistance, so it will show a negative temperature coefficient. That means, okay, the resistance is going to reduce. That is because N is going to increase. The electron or hole concentration is increasing with the increase in temperature. Okay, so that is why, because then the conductivity increases and resistivity decreases. So that is why it has a negative temperature coefficient. Okay, so this is very different from metals. Okay, on the metals, on the other hand, okay, if you increase the temperature, resistance decreases. In the case of pure semiconductor or intrinsic semiconductor, if you increase the temperature, resistance decreases. So if you are given a material, and if your question is like, how do you distinguish between whether it's a metal or pure semiconductor, all you need to do is that you vary the temperature and you measure the resistance and look at what is the temperature coefficient. If it is positive temperature coefficient, it's metal. If it is negative temperature coefficient, it's a intrinsic or pure semiconductor. And for silicon, okay, actually, if you look at this number at 300 Kelvin, okay, it will come out to be roughly around 10 to the power of 10. Okay, so this number also you should try to remember. Okay, it's around, okay, it may not be exactly 1.5, it's around 10 to the power of 10. Okay, so so this you should remember, right? So in silicon, actually, and we earlier saw what is the silicon atomic density? It is 5 into 10 to the power of 22 per centimeter cube. If you look at the number of free electrons, okay, it's actually at room temperature, it is only 10 to the power of 10. That means if you take this ratio, it is 5 into 10 to the power of 22. Okay, it is like 1 power 10 power 12. It is like 1 parts per trillion, right? So that is why if you take a pure semiconductor, it is as good as an insulator. So you will see only one free electron. If you scan only like a trillion atoms among them, you will see only one free electron. So that is why the resistance or the resistivity or a pure silicon, okay, it is very large. Now let us come to this one. Okay, actually it comes from it's again chemical thermodynamics. Okay, it's actually called as law of mass action. Okay, so it is analogous to chemical reaction. Okay, so the NP product. Okay, so the NP product, you take the product of electron concentration and the hole concentration. What it says is that the product should be independent of the concentration. It only depends upon the temperature. So for example, that is because, okay, the electrons and holes, okay, you can write like a chemical in the chemical reaction, the reversible chemical reaction. So the electrons and holes are always formed by, okay, we saw this one, right? Okay, in order for an electron to hole to form, okay, you need an valence electron from the valence band to go from valence band to conduction band. So it will always create, okay. And similarly, we will see later something known as recombination. If an electron can come from conduction band to the valence band, it can recombine with the hole. Okay, it become an electron in the valence band. So the generation and the recombination, generation or the electron hole pair generation or recombination, it always happen in these materials. In this case, okay, through pairs. Okay, so then you take the product of N and P. Okay, N and P here. Okay, so we can take the product. Use this expression here. You take this expression here, right? So NP will be, okay, you take the product, okay, it will be always Ni square. This is an important consequence, okay, about Ni square. So that means NP is equal to Ni square. Okay, we will see, okay, under what condition this is valid. So here is an exercise for you. Okay, so earlier we wrote that, okay, N is equal to Nc exponential minus Ec minus Ef by Kt, right? And similarly, P is equal to Nv exponential Ef minus Ev by Kt, right? So the thing is that, okay, so you eliminate Nc and Nv and you write N as a function of Ni. Okay, Ni is this one and P as a function of Ni. Okay, so then, okay, so I'm sorry, this is actually Ef, these are subscripts, okay, Ei minus Ef like this one. And this result actually is also a very important result. Okay, you have to remember that NP is equal to Ni square. It actually holds true. It holds true. Even in the next class, we will see about extrinsic semiconductor. That is what happens when you dope the semiconductors. But this approximation, this NP is equal to Ni square is valid. Okay, is only when the Boltzmann approximation is true. That is because we derived this quantity assuming Boltzmann approximation. That is this is Ec, this is Ef, and this is, suppose this is Ev, this is Ef. Okay, as long as Ec minus Ef is greater than 3 Kt, and similarly this is also 3 Kt. Okay, then only you can write this, the electron concentration, the hole concentration, this one. Then only when they multiply, okay, it will multiply, it will cancel all the exponentials, you get Ni square like this one. Okay, so this NP is equal to Ni square, the law of mass action, it holds true only when the Boltzmann approximation is valid. Okay, that is very important. I'm sorry to say. Alright, so now let us see what we have studied today. Okay, so this concludes the topic of all the solid state physics. Okay, we went through the crystal structure, where we saw what are the directions, the crystal orientations. Then we studied about the quantum mechanics. Okay, we saw in the infinite potential well, and the finite potential you have different discrete energy levels. But when we go into the periodic potential well, you have all these discrete energy bands and gaps. Then we saw about the effective mass approximation. Okay, so effective mass approximation allows for an electrical engineer to do all the device analysis without knowing anything about quantum mechanics, because all the information about the quantum mechanics and the periodic potential is encoded into the effective mass. So the price we have to pay is that, okay, you need to use different effective mass for different materials. Then we discuss about the Fermi level, right? The Fermi level, it lies at the topmost occupied state for metals. But for materials with a discrete energy level, so the discrete bands at 0 Kelvin depends upon between it is exactly between the topmost occupied level and bottommost unoccupied level. And using then we saw the concept of density of states. Okay, how many possible states are available as you move higher in energy. Then using the concept of density of states and Fermi level, we calculated the number of electrons in conduction band, and similarly the number of electrons in the valence band. And we calculated the electron and hole concentration at equilibrium at room as a function of temperature. Essentially, it depends upon the band gap. Okay, that is very important. As the band gap is large, you have a smaller number of electrons. So this is this number is roughly around 10 to the power of 10 for silicon at room temperature. And the last one is about the law of mass action. So this is essentially the NP product. Okay, NP product NP product is actually equal to Ni square at that temperature. So N of any temperature and P of any temperature is equal to Ni square at that temperature, right? This is valid as long as the Maxwell-Boltzmann approximation is true. That is, when your EF, the Fermi level is at least 3 kT away from the bottom of the conduction band or 3 kT away from the top of the valence band. Alright, so in the next class, what we are going to do is that we are going to take extrinsic semiconductors. Okay, so that is so if you have pure semiconductor, okay, there is not much use. Okay, you can use it like a piece of resistor. But in order to make semiconductor devices, we need to make it an N-type semiconductor or a P-type semiconductor. Now we will see. Okay, now we will see how to calculate that. You can use the same expression for the electron and hole concentration for extrinsic semiconductors. The only difference is how to calculate the Fermi level. The Fermi level, in the case of intrinsic semiconductors, we saw it is exactly at the middle of the band gap at 0 Kelvin, and it stays very close to the middle of the band gap even at higher temperature. But in the case of an N-type or a P-type semiconductor, we will see that it is no longer true. Okay, for the Fermi, you can actually move the Fermi level along anywhere inside the band gap when you vary the doping. Okay, so that's what we are going to see in the next class. All right.